Great. So yeah, if you remember last week, we started talking about anomalies um, as a tool for, I guess, diagnosing degeneracy in the ground states of our system and noticing that sometimes when we do have this ground state degeneracy, that suggests there's something with an anomaly going on. So it's something we'll explore over the next few talks. And remember, we mentioned that, in general, in like a quantum mechanical system, degeneracies in the ground state are actually quite rare, because we don't have things like spontaneous symmetry breaking. So we don't have this set of degenerate ground states that we can pick out. The quantum system sort of spreads over all these would-be degenerate ground states to get a true ground state. Um, so I guess, yeah, so this time we're just going to, yeah, just introduce inflow for the first time. And then next week we'll return back to some of the examples we were talking about before. If you remember, we talked about like this idea of the particle on the circle, where we had some periodic sort of potential, and we said that at particular values of the potential, um, or a particular choice of like theta to describe this potential, we have a ground state degeneracy, and this is related to an anomaly. And we'll see next week how this relates to inflow. Um, so yeah, today won't be that long, but if people want at the end, I can maybe talk about some other examples of anomalies. But otherwise, yeah, let's get started then. So let's start by looking at symmetries. So, as you may know, um, the basic idea when people think of anomalies, they think of an anomaly as something that's an obstruction to gauging a theory. Um, why is that? Because we have a symmetry of the classical theory, and it's not a symmetry of the quantum theory. So if it's a gauge symmetry of our classical theory or a gauge redundancy of the classical theory, um, then in the quantum regime, if we have gauge symmetry breaking, which, we can't have a gauge symmetry be broken, then that suggests there's something wrong with trying to gauge the symmetry in this theory. Okay, so in general, we separate symmetries into two types. We have space-time symmetries, and we have internal symmetries. Um, and usually what we do when we have a symmetry, we have a conserved current, right? And then what we can do is we can introduce some classical background field. I'll just call this J alpha, where alpha is going to be a multi-index. So maybe multiple indices there. Um, and we can then couple this current to a classical background field. Uh, so then we get some term that's like this. So for example, if we have compact Lie groups, um, these sort of background fields are connections, and they tell us information about the bundle topology. Um, so we have connections for Lie groups. If we have finite or discrete groups, so if you remember, we've been looking at things like Z2 and Zn symmetries. Um, these give us flat connections, and they tell us information about defects. So things like domain walls and stuff like that. Of course, if we have Lorentz symmetry, then we have a metric. And we also have things like fermion number and time reversal symmetry, and this tells us stuff about the spin structure or the orientability of space-time, and not just the orientability, but the higher invariance related things like spin structure and the ability to have fermions on the particular manifold. So then what we can do is we can write some partition function of as a functional of these classical fields. Now, what we want to do is consider taking this symmetry and promoting it to a gauge symmetry. So instead of a global, we now consider it as a local symmetry. And this means that in general, our our background fields, whatever they may be, are going to transform some way in terms of some gauge parameter lambda. Of course, you have the very familiar transformation for like a Maxwell gauge field. We know this goes from A mu to A mu plus del mu lambda, right? If we have, gravity, you could have the metric transform by a diffeomorphism, um, which we can like parameterize as something like this, right? Some infinitesimal diffeomorphism. And this is like generated by like your Lie derivative and stuff like that, if you've seen that before in general relativity. So if this is a gauge symmetry, then it should be redundancy of the system. So our system should be completely unchanged by this transformation. So in other words, our partition function should be equal for the transform field. So I guess in general, the question is this true? For a general gauge symmetry in a classical theory we're familiar with, is the path integral, so the full partition function, actually invariant under this transformation? So let's think about a U1 symmetry for a moment. And let's think about it topologically as we have been doing. So let's think about if I have some space time, then we know that this symmetry can be represented as a codimension one operator. So if I have this space-time here, if this is, I guess, some 3D space-time, I can insert this this U of G, where G is some group element, as some codimension one operator. So I'll consider this surface, and let's suppose this is like the time direction, and let's suppose this is like inserted at t naught. Now, if we want to consider like the world line of a charged particle or something, we can think about like a Wilson line. So let's say we have a Wilson line of some particle, or just a Wilson line in general. So I'll say this is a Wilson line. Now, um, we want to well, we can see that because this is a codimension one surface, if we have this infinite extent Wilson line, then we're going to have to intersect this surface at some point. So we have these two different extended operators intersecting somewhere. Okay. So what we sort of expect is when we have this topological operator, if it's a global symmetry, we expect, particles and stuff to transform by a phase under this U1 symmetry. So if we think about um, if we think about this Wilson line as some integral over some curve, right? And we'll just say it's like this infinite line. Then when we apply this U1 symmetry to this operator, we expect some sort of transformation by some group element, right? Um, So equivalently, we can think of that as a transformation of the connection. Um, I'll call this, I'll say this is some A prime, and this A prime um, can then be given by this sort of delta function um, at this point here. And this means that nothing sort of happened. So if we then want to, say, shift this defect surface to some other point, right? We can think of this as a gauge transformation by some parameter lambda, where lambda is given by this heavy side. Um, right? And then clearly you can see that A plus d lambda, you take the derivative of this heavy side becomes a delta, this heavy side becomes a delta, this delta gets cancelled, and we've shifted it to this new, let's say, T1. So these sort of singular gauge transformations that shift our surface around, um, if that makes sense. So in terms of our partition function, if we have ZA,
So Jesse, just quickly,
yeah,
um, with the xi integral gamma a, and then you have it on the right hand side equals xi a dash.
yeah,
Um, I'm just trying to think. That's also meant to have a in the a dash in your definition of a dash.
yeah, but let's just assume it's taken around like A equals 0 or something. Yeah, that's
Okay,
correct.
so it's
Yeah,
around
yeah,
a
yeah.
zero.
Um,
If a is not zero, then
I mean, yeah, it's the same thing. The point I'm trying to emphasize more
yeah.
is the idea that that this we get changes in our description
Mm,
because we have these operators become coincident. So if these were like topologically separated operators, wouldn't be a problem. But because these operators are intersecting, then we have some sort of breakdown here, right?
okay. Just one other thing. Is that phi? Is that a dash equals phi?
Yeah, I used a
Oh,
different.
so it's
Yeah,
yeah, it's the
sorry.
same one.
Yeah,
That's
yeah.
okay.
I mean, you can think of this as you can put this as an integral of phi delta, whatever the
Mm-hmm.
location is, right? That's all
Yeah.
that's happening here.
Yeah, that's fine.
Yeah.
And then also you're treating this as a the global parameter rather than say like a local
Yeah,
function
yeah, yeah, yeah.
as we would do for gauge theory.
Yeah, yeah. So yeah, the idea is, yeah, things are non-trivial when we have these topological surfaces intersecting. Um, and we can see that, yeah, by shifting around these surfaces, we get um, a different transformation of A. And these are singular, what they call in the literature, singular gauge transformations.
Do you know what to use the word singular is? I mean, like, what's the
Yeah, because it's got
singularity? Is that
like
from the Hindu stuff?
yeah, it's got the delta
Oh, just from
functions
the
and stuff.
delta.
Yeah, 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 yeah.
Cool.
I think they use it a lot in lattice stuff when they talk about vortices and like twelve lines and stuff.
Okay. Cool. Yeah, thanks.
Yeah. So yeah, so the idea is that when we have if we have the partition function change under some gauge transformation, this is going to be related to some topological breakdown. So when we have, well separated defects, if we had a Wilson line like this, nothing goes wrong. But when, if we had, I guess, some intersection, then something can go wrong. The same thing is, if we had just quantum mechanics, right, in 1D, if we had two different operators, G and H, everything works fine with they're topological, they're separated, but when we bring them together, we don't know what's going to happen. Um, Before we talked about these uh, these operators that obey group composition, but this doesn't actually have to happen. Some other complicated behavior can happen. In general, we get a sum over elements. And this will make a bit more sense once we start looking at these things under correlation functions. And we'll see it's actually quite natural how these things emerge. Okay, so okay, let's say that our partition function is not equal under gauge transformation to our original partition function. But let's make a guess and say that it transforms in a very particular way, such that everything just changes by a phase. And we'll say it changes by phase, some function that's related to our gauge parameter and our background field. So, for example, again, if we look at the U1 theory, we know that um, over our manifold X, we have our current is coupled to our background field, right? And we can think about what happens under some gauge transformation. We know that our gauge field is going to shift, right? And we can do partial integration to move this derivative over. So, um, so that now the derivative is on this current. And normally, we just go, oh, yeah, well, this is current conservation, right? The derivative of this current should vanish. That's by definition of a conserved current. But if we think about this, like this is true when we don't have operators inserted, right? Um, if we think about this picture again, if we pick some surface, what we were doing before is we would consider something contained in between these surfaces and what happens on one surface and the other surface between them. When we take these two different surfaces, the current doesn't change. That's current conservation. But when we had operators inserted, when we try to drag this topological surface to sort of contract it with this one to a point, like remember we want to shrink these down. If we have an operator inside, then something can go wrong. So when we have these operator insertions, things might not behave so well. So more precisely, when we don't have operator insertions, the statement is something more like this. But when we have operator insertions that are, I guess, outside these surfaces, uh, we'll just imagine we have however many of these operators, then indeed, the correlation function vanishes. But if we have x equal, yi for one of these um, operators, then maybe we have some contact terms. So it may pick up some contribution from some delta function, right, when these operators become coincident. So I guess the idea then is that we want to think about how this might affect our partition function. So another thing to notice as well is that when we have this partition function, we actually have an ambiguity. We can also add a phase to this partition function independent of this idea of anomalies, which is given by some function of our background field. And this is called a scheme, and picking a different function is called a change of scheme. And I guess the idea is that this doesn't really matter because at the end of the day, when you divide, like if you want to actually like compute something, you divide by the partition function. So this excess phase sort of cancels out and doesn't really affect things. So because we have this choice of scheme,
Wait, so could you just say quickly, how do we choose the scheme? So the scheme, the beta scheme.
yeah, you just think of it as like a phase that can cancel out, right?
Oh, okay. Is it just saying like we can write our gauge symmetry in terms of the scheme parameter?
So this isn't the gauge symmetry. This is saying
Mm,
just with our partition function, we have the
yeah.
freedom to choose a phase, basically.
We can choose a phase, but it's not a gauge symmetry.
No, uh
Oh,
this
like
is just
I'm
yeah,
thinking
this
like a
is like
gauge symmetry of
no,
the partition function, whatever that would be.
mm, it's more like it's more like a choice of normalization,
Mm.
I think is the best way to think about it.
But like choice and normalization as well, in the case of just like finite dimensional quantum mechanics, is a gauge symmetry in terms of the complex phase.
Sure, sure. I think yeah, you should just think of it as a phase you can choose, right?
Hmm.
A phase that cancels out in this when you do actual computations.
Yeah, okay. I guess the thing to say about maybe the difference is that with quantum mechanics, you're choosing the gauge symmetry on the one I was talking about, you choose it on the particles,
Yeah.
on the states in the Hilbert space. Whereas here, this phase is not a phase of the states in the Hilbert space, but of the partition function, which doesn't really make sense, I understand, to describe it as a gauge symmetry in the same sense as the other one.
Well, it's not really like a
But
gauge symmetry because it's not like a local choice of phase, right? It's just
hmm.
one number that you can pick, basically.
Oh, true. That's a good point. It's this global
Yeah.
ambiguity. Yeah,
Yeah.
that's okay. That is a good point. Um, yeah, and it's not really symmet. Is it a symmetry? Would you call it a symmetry in this case?
Um, I mean, not in a meaningful physical way, right? It's
Yeah.
yeah, it's not like you have conserved quantities or something associated with this. It's yeah,
Well, yeah, the conserved quantities only really comes from Nerva's theorem, which means you need a Lagrangian or Hamiltonian, or a no, sorry, that's incorrect. You need a variational problem to have Nerva's
sure.
theorem to get the conserved quantities, but there is no variational problem here.
But I think it's best to just think of this as some normalization.
Yeah, sure. I'm just trying to think about how to connect it to other things. That's fine.
But
Um,
yeah,
yeah, do you have an example for, say, like how we could choose beta?
uh, I haven't in this, but maybe next week there will be one. I haven't checked.
Yeah, okay.
Um,
That's
but
fine.
I think it doesn't matter so much because the idea then is because it's beta of alpha, then under gauge, then we actually do change beta, right? Because it's some function of alpha.
Mm,
Um, so this means if we want to talk about the anomaly, I guess this anomaly functional alpha, then really what we have to do is look at alphas where we identify um, alphas uh, that are equivalent to we identify alphas that are the same up to a shift of this choice of scheme.
yeah.
So this sort of identifies like the inequivalent alphas because I guess yeah, if we have this other ambiguity where we can choose the scheme, then then what's really physical is the stuff that we can't shift away by this choice of scheme, right? So then this gives us a cohomology of anomalies, right? So hopefully you can see that through this identification.
Yeah. Um, One question as well. Let me just think.
Yeah.
So before, like, for example, if you scroll up and you go to the section, let me just think, where is this? Let me find this. I saw you wrote it somewhere, but let me just find it in like the notes I wrote. Oh, it was just below the fusion of the two things. So you had the fusion and you were saying they were non-invertible.
Like this.
Yeah. So down below you have the Z A of lambda, so that's going to be the gauge transformation. You say it picks up the phase.
Yeah, this is like sort of
Gen
an ansatz.
Yep. So generally this would be say like when I for the chiral ABJ one, when
Yeah.
you do the measure transformation, you see that you get the exponential, and then this term that you wrote there
Yeah.
is the anomaly term, and in
Yeah.
particular it's the ABJ one.
Yeah.
Is that is there a connection? But so I would call that the anomaly phase or something like that.
Hmm.
Is there a connection between that and the scheme thing you wrote just below?
I mean, the idea is that um
Like, are they the
this
same thing or different?
different, right? Like
Different.
they're
Okay.
different because of this. But the idea is that this is really we have the freedom to, I don't know, change the phase by some local uh functional of this. Um so this is something that doesn't really I guess affect the theory, right? It's some other functional. But then the idea is that with the anomaly,
Yeah.
um, it really comes from how like the measure transforms in this here, right?
Okay.
Because this
So there's
ZA has, some integral over the fields. This thing here is just some extra phase.
yeah. Freedom to choose. Let me think about this. Okay, so for example, let me think about this. In principle, you could have an anomaly which would appear to be something which would appear to be anomaly, but then you could have it in your system that the anomaly wouldn't be an anomaly because it would be deleted by the beta scheme term
Yeah,
because it would be,
but
yeah.
yeah, potentially you could have something that looks like an anomaly, but actually
Yeah,
because it's
yeah.
equal to I guess like we can describe it in terms of some variation of some local beta,
Hmm.
then it's actually identified with the zero anomaly.
Yeah,
So that's what I mean by like a cohomology problem, right? You
I see.
yeah, you have these different choices of alpha, and they're identified based on whether they can be removed by a shift by some local beta.
Oh, that's really
Um,
interesting. Yeah, cool.
I'm trying to think if there's some simple example, but if we want to discuss it after, I can also I have some notes on some group cohomology stuff, um, where you
Yeah,
can
that'd be really
construct
interesting.
some
Yeah.
sequence, but I wouldn't claim to have a full appreciation of the technical details. But it is quite nice. Um, this ansatz seems a bit random, but you can actually show it
Hmm.
occurs quite naturally by looking at like Maxwell terms and Chern-Simons terms and Wessamino-Witten and
Just you mean the
something
anomaly
else.
ansatz?
Yeah, you can construct some I guess some lattice of like sequences in the algebraic sense, and you can show like some nice relationship where this phase emerges naturally. But um, I haven't included it here, but we can talk about it after if you're super interested.
Yeah, it'd be very interesting to go through.
Yeah,
But thank you. Yeah, that's great.
yeah, yeah. Yeah, so I guess yeah, the idea is that we have these equivalence classes of anomalies. That's the takeaway. Okay, so now let's look at the inflow perspective. So we've been working on some manifold X. So now let's consider some manifold Y such that the boundary of Y is equal to X. So before we were working on X, and now let's consider, some Y, which is like a bulk, and such that our theory that we're talking about lives on the boundary. So then if we did this, then we could write a partition function for um, the manifold Y, um, and we can write it as something like this for some omega of the gauge fields or the background fields. So then what we can do is we can look at the difference of, I think I messed something up with my notation here. Um, we can look at the difference of this function, well, some sort of difference of this under gauge transformation of A. So what I'm going to do is I'm going to look
Oh,
at,
sorry. What is is it omega? What's
yeah,
omega in this case?
just some function.
Oh, some like differential form.
Yeah, some no 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 no, just like
Yeah.
just some functional of alpha of A, sorry. This is like a yeah, some like partition function, right? It's the same thing as we were doing with like the betas and the alphas before.
Hmm. Um, I see. Oh, so is this meant to be like what would you call the effect? Like the
Yeah, you can think
uh
about it like some action or something.
yeah, the effective
Or
action. That's the word I'm
yeah,
thinking of.
something like that. Yeah.
Okay. Um, yeah, and then there's meant to be integration of volume element, right?
Um, no, we're just gonna keep it like this, actually.
Okay. Because I'm assuming that you mean, like to do an integral, you have to have a
Yeah,
volume
yeah. But
element.
we're going to be sort of thinking
But
about
what's happened to that?
we're going to be thinking about this in terms of like these phases, right? We want to relate it to these guys,
Hmm.
or rather to these guys.
But to have an integral, I mean, I guess this is what I'm confused about. To have an integral, don't you have to have like a form associated with it in which you integrate over?
Sure, like just imagine there's yeah, whatever form this needs to be for your
Oh,
manifold.
yeah.
Yeah,
So to be like the volume form
sure.
with it
Yeah,
as well.
yeah,
That's fine. Or you could treat omega as having the volume form
yeah,
um
yeah.
with it
It's
as
just
well.
some arbitrary functional of A that you can integrate over.
Yeah, that's fine. That's fine. I just wanted to check that.
But what we're going to do is we're going to define it so that under these gauge transformations, it's equal to our anomaly that we picked up before. So how does this sort of work? The idea is we want to take our x and we want to consider like evolving it over time, right? So let's consider x times, some interval. Say x times the interval, or we've got an interval, for example, 0, 1. And what we're doing is that while we move x along this interval, we're going to start with our configuration A, and as we evolve it in time, we sort of apply our gauge transformation. Okay? Um, so in other words, A of t equals 0 is A, and A of t equals 1 is our gauge transformed field. Okay, so remember we wanted some y such that the boundary of y is equal to x. So what we can do is we can take these endpoints and we can glue them together and identify them. So then this will give us something that looks like x times an S1. Okay, and then we'll say this is our y. Um, so this is what we call the mapping torus construction, right? So we've sort of extended our theory into a higher dimensional space, such that we have um, our theory still living on the boundary. Okay, so then this means that in terms of our anomaly functional, we can write this as the integral over this other manifold y, like this. Okay. Um, and this captures the anomalous phase. So we can construct some higher dimensional theory with x as our boundary, such that this bulk theory um, has, I guess, this phase which can cancel out the anomaly. So what we can do then is we can define a new partition function, which is going to be equal to our original partition function. And I think I actually want a minus sign in here, right? Okay. So this is a modified partition function, but now it is also gauge invariant by construction, right? So when we transform this thing will pick up this picks up some alpha phase, and this picks up the opposite phase, and then we get something that's invariant. Um, so the idea is that we have something gauge invariant, but we've paid the sacrifice of now having to consider our theory is living on the boundary of some bulk theory. So we have a higher dimensional theory from which the anomaly flows in. So this might seem a bit bizarre, coming from, um, if I have a 4D theory, are you really saying that we're actually living on a 5D theory and we have the anomaly flowing in? But what's actually like quite natural is to think about this maybe in a lower dimension where if we have, um, for example, I guess, some 2D sort of surface with a boundary. We know that in like a presence of a magnetic field, there is an anomaly of like this theory if we have like chiral fermions or something if we have fermions, for example, and we know we get some chiral anomaly, and we know that the full theory that we actually need to consider is actually, this bulk plus some theory living on the boundary, right? So if I have like fermions on the inside, we also have to consider, um, I guess these are left moving or right moving chiral fermions, a theory living on the boundary. And maybe this is like a very familiar sort of example. This is like quite a common example, is that, yeah, we have this bulk theory that has an anomaly, um, but we know this bulk theory has a boundary. And to get the full theory that doesn't have an anomaly, we also need to consider excitations on the boundary. And we know these are chiral fermions living on the boundary. This is like the quantum Hall effect sort of stuff, if you've seen it before. So this stuff actually does actually emerge in practice. So even if it might seem bizarre thinking about like a 4D theory with a 5D inflow, when we actually look at these real systems, um, you really need to consider the bulk plus the boundary to get something that's anomaly free. So that's actually all I had planned for this week. And then I guess next week we'll return to looking at the particle on a circle and seeing how we can look at that as like a boundary theory of some higher dimensional bulk theory and see how that works with the anomalies. And I guess that will give a practical calculation of all these different terms. But yeah, other than that, I think that's all for today. But yeah, I'm happy to discuss anything else.
Oh, yeah. Thank you, Jesse. I just have a question about the mapping torus construction. Could you
Hmm.
scroll up a bit? So, okay, so you define your partition function to be like say the d plus one dimensional one over y, and then in the line below, what ex could you repeat what exactly are you doing in the thing below zy? So you have
Um, like here.
yeah, the thing where you just write exponential I
Yeah, so we're
y
just saying
omega alpha.
we want to relate this omega to our alpha in some way. So this sort of like tells us, I guess you can think the correct
Okay.
Lagrangian or the correct action or something in that
Yeah.
vein of thinking, right? Because we want to construct a bulk theory that can cancel out this alpha.
So is this saying like, is this a desiderata? So you want this to be true, or is this like,
Yeah, I think that's the correct way of thinking about it. Yeah.
yeah, you want it to be true. Okay. Um, hmm.
Yeah. I
Okay, I'm just
mean,
trying to think about this. And then you're applying some sort of Stokes theorem-like thing. Is that right? Or there's implicitly meant to be a Stokes theorem?
um,
Am I picturing this right? I'm just thinking about how you go from the higher to lower dimensions, and it's basically looks like some sort of like fundamental theorem of calculus type things where you have the boundary.
yeah, yeah.
Yeah.
Um, I mean, I think the idea is that it's more about like matching these phases.
Um, sure. But like I guess perhaps we need to look at a proper example to actually
Yeah,
understand that.
I think next week, when we look at the circle
Mhm.
example, it's maybe a bit more transparent,
Mm.
because then you can literally see what the phase is. Um, yeah, like they explicitly compute what the phase is, and that tells you exactly how to modify the partition function. So you'll see exactly what these things are, right? So, for example, you're going to get some sort of alpha that looks like maybe something like this, and then this gives you an omega that looks something like this, for example.
Yeah,
But we'll see. We'll
okay,
go through that example next week.
I see. And then also on your diagram, would you be able to clarify? Okay, so A is on the X, is A on X? Like
Yes,
A,
A is a
yeah,
field living on X. Yeah.
okay. So A is on X, Y is in the center between them. And then what is the difference
So
between a top gluing and a bottom gluing? So you have just like a line interval and the bottom one's meant to be a
so
circle.
so the idea is that I'm evolving this whole sort of surface in time,
Yeah.
and then I'm identifying the start and finish of my interval. So I'm turning the
Oh,
I
okay.
into an S1.
Oh, I see. So you evolve and then say, actually,
Yeah,
we want to get back to the start.
yeah. This is like because specifically I want, the boundary of Y to be equal to X.
Yeah.
So if I didn't do this gluing, S1 has no boundaries, but I
Mm.
does have boundaries. Because otherwise I would get something like this, I guess, right? If
Yes,
I do the
indeed.
identification. Yeah.
Yeah.
That's the idea.
So, so identify start and end. Okay.
Yeah.
Um, that makes sense. Let me just write this. Yep. So you identify is through. Cool. Okay, that makes sense. Um, yeah, I'll let other people think if ask any questions, but I'll just keep thinking about if I got further things I want to ask.
I can also yeah.